Hello everyone, welcome to the lecture 7 of the course Diffusion in Solids. So in the last couple of lectures, now we have built a foundation of solving the equations which arise in the diffusion related processes or problems. So we saw the Laplace transform, we saw the fixed laws, and now we also saw in the previous lecture that how do we use Laplace transform to convert the fixed law from a partial differential equation to an ordinary differential equation. So now let us go ahead and solve some of the equations which we encounter in the diffusion related process. So this we will do over the over the course of next 3 lectures, taking various instances where such situations arise. So today we will talk about the problem of the steady state condition and about the thin film geometry where instantaneous source is involved. So I'll introduce you to each of these. So let us go ahead. So just before we go to the actual problem, I'll just tell you some general steps. So whenever we are solving the diffusion equations, there are some general points that you should remember. First thing, we have to understand the geometry of the problem. So like I told you in the lectures on the fixed laws of diffusion, that you can have the fixed law applied in different forms depending on the whether you are a Cartesian geometry or you have a cylindrical geometry or you have a spherical geometry. So like that, understand the geometry of the problem. Sometime also it is helpful to decide in which direction the diffusion is dominant, because many of the times you don't need the diffusion in one direction only is important, the other two you can neglect and therefore frame it as a one dimensional diffusion problem, which is much easier to handle. So therefore the first step is to understand the geometry of your problem. Then second is to identify the initial conditions. Before the diffusion process start at t is equal to 0, let's say, how is the concentration spread in your sample? Okay, so that is what comes under initial conditions. When I say the initial, it means that t is equal to 0. Then you go to basically the next is very important to identify the boundary conditions. Boundary conditions are the conditions which will usually be applicable across the at the boundary of the system for all the time. So typically the boundary conditions do not change with time. So boundary conditions means, suppose if I have geometry, then or let's say a plane sheet, it should be valid at the boundaries of the system. So this kind of the boundary conditions we need to identify. And then once you have all this, then you can choose which form of fixed law I should apply. So basically you want to apply fixed first law, you want to apply fixed second law, and if whatever you choose in which coordinate system I should apply, is the Cartesian system good enough for me, or should I apply it in a cylindrical system? That will also depend upon the problem that is in our hand. So with this, now let us go to the first problem. So which is, hydrogen gas is passed through a planar membrane of thickness L. At the steady state, the concentration of hydrogen on inner wall is maintained at C1, while at the outer wall it is maintained at C2. What will be the concentration of hydrogen at L/3 distance from the inner wall, and what will be the value of the flux at this point? So now let us see the 4 steps that we outlined last time, and this is how the problem looks like. So this is a hydrogen where this is your planar membrane. Inside the wall or the inner wall, you have the concentration at C1, outer wall you have the concentration at C2, and it is maintained. So C1 and C2 are not changing, and C1 is greater than C2. And now our intention is to find the concentration of hydrogen at L/3 distance. So what we do, the geometry is a planar sheet. So we can apply our xy coordinate, and the diffusion is only happening in one direction. So we can assume to be a one-dimensional diffusion. And since it is in a steady state, in this particular case, the initial condition, the intermediate, final, everything is same, because nothing is changing with respect to time. Now, what are the boundary conditions? So, boundary conditions, if I take my origin at the inner wall, then this is my point of x equal to 0. So, at x equal to 0 comma t, that means c is defined as x, c is written as x comma t. So, c at 0 comma t is c1, and this is always maintained. So, you see, I told you that the boundary conditions are usually independent of time. And then c of L comma t is c2, which is the concentration at the outer wall. Now, as I said already, for planar sheet, we can use Cartesian form of Fick's first law, and one dimensional is enough. So, Cartesian form of Fick's second law, sorry, not the first law I meant. So, since diffusion, let us take in x direction alone, we see that dou c by dou t is equal to d times dou square c by dou x square. Since it is a steady state, I can write dou c by dou t as 0, and therefore, d times dou square c by dou x square is 0. So, any derivative when it is 0, it means that dou c by dou x is equal to k1. Then only you can write dou square c by dou x square as 0. So, dou c by dou x is equal to k1. And now, if I integrate it further, I can write c of x comma t is k1x plus k2. So, this would be my integration constant. How do I find out now k1 and k2? So, to determine k1 and k2, what we need is our boundary conditions. So, our first boundary condition was c of 0 comma t is c1. So, if I put here, this is c1 is equal to, this term goes to 0, and we have only k2. So, basically my k2 is c1. And then if I put c of L comma t is equal to c2, that means I have c2 is equal to k1L plus k2 is already c1. So, I get k1 as c2 minus c1 by L. And if I put the values of k1 and k2 here, what I get is c of x comma t is equal to c1 plus c2 minus c1 by L times x. I hope it is clear. So, now we remember that we got this expression c of c is equal to c1 plus c2 minus c1 by L into x, and our problem stated that we need to find the concentration at L by 3. So, I put x equal to L by 3 here. So, c at L by 3 times t, I get c1 plus c2 minus c1 by L into L by 3, which gives me the value of 2c1 plus c2 by 3. Now, to evaluate the flux, J is equal to minus d by into dou c by dou x, which is dou c by dou x is equal to nothing but, if you see the expression for c, this is dou c by dou x is nothing but c2 minus c1 by L. So, here you can write that c2 minus c1 by L, and therefore, J is equal to minus d times c2 minus c1 by L. And if I represent this graphically, then I can plot C as this is a linear decrease. So, from C1 to C2, because it is a linear decrease of x. You just have to remember this, that here it is C2 minus C1. So, it is a negative quantity. That is why you see that the line has a negative slope here. Okay. And then if you plot J, J is actually independent of x. So, that is why you get a constant line here. So, this flux is independent of x. Now, you actually, if you carefully observe, you will see that we could have arrived the expression of flux for flux through an alternate and much faster way. Can you think how? Let me know in the forum if you can find out a much faster way to arrive at J. Now, let us now go to the non-steady state diffusion, which is much more common actually, and let us see this problem. So, the problem is like this: a thin layer of element B is sandwiched between two blocks of element A. Then the assembly is heated isothermally at a temperature T for a time small t. And what we need to do is to estimate the concentration profile of B as a function of diffusion depth x and time t. And the total amount of B can be taken as MB. The initial amount of B can be taken as MB. So now you have this is how the situation is. This is a thin layer of B. So this is what is known as a sandwich geometry. Okay. So remember that this is exactly at the center. So the dimension of A on the both sides are equal. And so if this is isothermally heated at temperature T and for a time small t, then you will see the diffusion of B happening. And you will see that initially if somebody draws the B was concentrated only x equal to 0, then as the time progresses, the concentration of B at the center will keep coming down and the B will spread like this. So this is what is indicated in the profile, that at a shorter time t1 you had much higher concentration of B at x equal to 0, which keeps on reducing as you increase the time. And this here what happens also that B goes much deeper into the A. Such a source where the concentration keeps on changing with time and not remain at initial concentration, this is known as an instantaneous source. This is known as instantaneous source. So that means the source concentration is actually changing with time. And it is very clear that the concentration is changing with respect to time, and therefore it's a non-steady state diffusion. Now, here when we say the geometry of the problem, it is thin film because it is a very thin layer of B that is deposited. It is infinite domain. This is very important to know that it is infinite domain. What infinite domain means is that the diffusion depth, the depth to which B diffuses inside A, is much smaller than the dimensions of the sample. Okay. So diffusion depths are typically in microns, a few hundred microns at best, whereas the dimension of the sample is much larger, millimeters, centimeters, and so on. So the diffusion depth can be assumed, so it's a reasonable assumption to say that the diffusion depth is very small than the dimensions of the sample. What it does is, it allows me to treat mathematically these endpoints as minus infinity and plus infinity. See, when I write minus infinity and plus infinity, it's not your sample is infinite. That is not possible practically. What it means is the sample is large enough to make this assumption valid, that the diffusion depth is much smaller than the dimensions of the sample. So mathematically, the endpoints of the samples can be represented by minus infinity and plus infinity, and it gives us a huge ease in solving the problems, the mathematical differential equations. We will see how very shortly. Now, the initial condition is that C of x comma 0 is 0 for any x greater than 0 here. And the boundary conditions are that at the end members, or not the end members, at the end points of the system, which is minus infinity and plus infinity, you see that C of minus infinity comma t is 0, C of plus infinity comma t is also equal to 0. So here, because we can treat or this assumption is valid, so I can write it as minus infinity and plus infinity here. Because the diffusion depths are smaller, so at the far end of the block A, the B does not reach and the concentration of B there is 0. Now, therefore, this are the boundary conditions. There is an initial condition which is that let us say initially you started with B with a some amount which is MB. Now at any point, if somebody has to measure what is the total concentration of B in my entire setup, it will not change because there is no reaction that is happening and B is not getting evaporated. So whatever B was there initially will be there spread across the both blocks of A. Therefore, what I can write is that MB, which is my initial concentration, is equal to minus infinity to infinity integral of Cb x comma t dx, assuming a unit cross section. So dx into unit cross section is volume, C is basically moles per unit volume, and this if you integrate across the dimension of the sample, this you will get the number of moles or the amount is same as the what was initially deposited. So basically this was the law of conservation of mass, and then very clearly it is non-steady state, so you can use the Fick's second law. Now this is the Fick's second law, and remember that now this is in this case we can use only the one dimension, we are considering the diffusion only in one dimension. So now how do we solve this? So to solve this, we use the Laplace transform of the Fick's second law that we derived in the previous lecture, because remember the Fick's second law as such, dou C by dou t is equal to d times dou square C by dou x square. That is a partial differential equation which involves two variables t and x. So what we did last class is transformed the Fick's second law into equation which is an ordinary differential equation which contains C bar, which is the Laplace transform. So that is dou square C bar by dou x square minus p times C bar by d plus C of x comma 0 by d is equal to 0. Now as per the boundary conditions, Cb x comma 0 is 0. So actually it should be initial conditions. Let me just try and correct it. So these are the initial conditions where Cb of x comma 0 is 0, and therefore what you will have is here dou square C bar by dou x square is simply p into C bar by d. Now how do we solve this? So this basically is applicable usually if you know for the exponential type of functions, satisfy this. Now here, because our geometry is from minus infinity to infinity, so you can write this as a into e power plus root p by db times x when x is less than 0, and b times e power minus p divided by db into x for x greater than 0. So here till now it was more general, so I did not use dB here, but now on we will use the term dB. Essentially it is same what we are representing. So for the x less than 0 there will be a plus sign, for x greater than 0 there will be a minus sign. Now the symmetry of the problem. This symmetry of the problem, you can see it suggests that it is sufficient to determine only either B or A. We need not go and determine. I mean, it's the same procedure basically. You'll get similar expression. So let us take the case where this function. So C bar x is equal to B times e power minus root p by db times x. Now how do we determine B? So you remember that initial condition we have already used, and actually it is the boundary conditions which determine this. Now to determine B, what we need to use is basically the expression that came from the conservation of mass, which is integral minus infinity to infinity Cb x comma t dx is equal to mb. By I can write this as 0 to infinity 2 times 0 to infinity Cbx comma t dx, and therefore this 2 can come down here and this becomes mb by 2. Now this may look a little bit more familiar to you if you remember the Laplace transforms. So what I do is now multiply the kernel of Laplace, which is e power minus pt dt integral 0 to infinity both sides. So what I have is basically like this. And now I can rearrange the integral a little bit and write it like 0 to infinity. Inside the integral, there is another integral 0 to infinity cbx comma t e power minus pt dt and a dx outside is equal to mb by 2 0 to infinity e power minus pt dt. So this particular integral what is inside is nothing but the Laplace transform of c, which is c bar. So I can write 0 to infinity c bar of x dx is equal to mb by 2, and this integral we know very well now that this integral is nothing but 1 by p. This we have already discussed a couple of times in the earlier lectures, but you can refer for a proof of that. So basically this integral 0 to infinity is 1 by p. So now we have integral 0 to infinity c bar x dx is equal to mb by 2p. And then from the equations 1 and the equation 2, what we have is, so basically if you just for your recollection, this is equation 2, and equation 1 is what we wrote in the previous slide here, that is the c bar x is equal to b e power minus root p by db into x. So if you use them both, then what you get is 0 to infinity b e power minus root p by db x dx is equal to mb by 2p. Integral of e power minus x is e power minus x, and this we need to divide. So this gives us minus b times root p by db e power minus root p by db x 0 to infinity is equal to mb by 2p. And this when I put x equal to infinity, this goes to 0. When I put 0, this goes to 1. So that gives me b is equal to mb by 2 root p db. And now if I put c bar of x is equal to mb by 2 root p db e power minus p root db by root db into x. Now how do I basically still remember that I have only solved c bar. So now how do I come to c? So just rearranging this a little bit more, I write it as c bar of x is equal to mb by 2 root db into e power minus. So I have just rearranged it a little bit. I write x by root db root p and divided by root p. Nothing, just a rearrangement here. Why I did that is to basically tell you, if you refer to the Laplace transform table which was given in the lecture 4, you will see that if the f of t is e power minus a square by 4t by root t, then the Laplace transform of that is equal to root pi into e power minus a root p by root p. What I have is this here in this solution. So you see carefully now that I have the expression e power minus root p by root p here, and a quantity a here, right, and multiplied by root pi. Root pi is not here, but root pi is a constant which I can always divide. So therefore, if you compare the RHS of this and RHS of this here, you will see that a is equal to x by root db, and therefore my solution, that means the original function, can be written as so the inverse of this expression is 1 by root pi. As I said, that root pi I can take down, multiplied by 1 by root t e power minus x square by 4 db t. So therefore the cb of xt is equal to mb by 2 root db root pi root t multiplied by e power minus x square by 4 db t. And I can write it more better as cbx comma t mb by 2 root pi dt e power minus x square by 4 db t. So this is how the solution is written. Here you will see this is what is known as a Gaussian solution. Okay, exponential minus x square by 4 db t. And if you plot this solution, what you will see is that so you will see at any time t, because it's an exponential function and it goes to 0 at minus infinity and plus infinity, you will see this kind of a distribution. It is maximum at x equal to 0, which is you can see for yourself. If you take a slope of this, so wherever it is maximum, the slope is 0 for dou Cb by dou x, and here, because there is a change in sign, the slope is maximum here and the minimum here. So you will see this kind of a variation for dou Cb by dou x. And similarly, you can also plot the derivative. So wherever dou Cb by dou x, this slope of this is 0, so it will be reflected in dou square Cb by dou x square as well. So here you will see that this is 0, and here it has a minimum. Basically here it goes to a minima. So this is how the variation of the Cb, its slope and its second derivative is sketched. Okay. So then in the next so now let us take another problem where basically it's very similar. A thin layer of element B is deposited on the top surface of the block of element A, and the assembly is heated isothermally at a temperature T for a time T. Now we have to estimate the concentration profile of diffusion depth as a function of diffusion depth x and time T. The total amount is again MB. So it is very similar to what we have, except that here you do not have one more block here. You have only one side where the diffusion is happening. So it is from 0 to infinity alone. Again, the similar conditions apply. It's a thin film, it's an infinite domain, because the diffusion depth we assume to be very, very less than the dimensions of the sample. And the initial conditions are C of x comma 0 is 0, B is only at the surface. This is for x greater than 0. And the boundary conditions, again the law of conservation of mass also applies. MB is equal to 0 to infinity Cb x comma t dx. And it's a non-steady state diffusion. We should use Fick's second law. Dou Cb by dou C by dou t is equal to dB dou square C by dou x square. Now, as such, you can also try and begin from the Laplace transform and try to arrive at this equation. But the geometry of the previous problem, which is the sandwich diffusion couple, if you compare, it is very easy to understand that the expression for Cb here is just 2 times what we saw the previous expression, because there the MB, that B amount of B was spreading into 2 halves. Now it is only going in the 1 half. So the Cb is at any point just the double of what you saw in the previous solution. And this is how the graph looks like. This is again a Gaussian solution, exponential function, and this is in fact the method which is used to experimentally determine d as a function of d at any given temperature. So you plot log Cb versus x square, and the slope of it actually gives you. So if you plot log Cb versus x square, the slope is equal to minus 1 by 4 dBt. And experimentally you can determine Cb x square, you know. So you determine the slope, and you know the time of annealing, so you can determine the diffusion coefficient. So thank you. Next class we will see a couple of more cases for solving the diffusion equations. Thank you.